Welcome to the Q&A session 11 from the playlist of electromagnetic induction. The topic for the today's session is the induced EMF in a solenoid due to the changing current. And this session is in continuation of the session number 9, in which we have studied about the self-inductance of a coil and the induced EMF due to the changing current. Now the question here is, a solenoid of 500 tons is wound on an iron core of relative permeability 100. The length and the radius of the solenoid are 40 cm and 3 cm respectively. So if the current changes from 0 to 3 amperes in 0.4 seconds, then the average EMF induced is. There are 4 options here and we have to find the correct one. And in this question we have to take the value of pi as 3.14. So in the session number 9 we have seen that the induced EMF is equal to L di upon dt, and this can also be written as L delta I upon delta t, where delta I is the change in the current in the time interval delta t. So in this question, delta I is known to us. Here the current is changing from 0 to 3 ampere in 0.4 seconds. So delta t is equal to 0.4 and delta I will be equal to 3 minus 0, that is equal to 3 ampere. So only thing which we have to find is the self-inductance of this solenoid. Now in the session number 9 we have seen that the self-inductance of a solenoid is equal to mu n square A divided by L. Here mu is the absolute permeability of the solenoid, and this mu is also equal to mu naught into mu r, and n square A divided by L. So A is the area of cross section of this solenoid. L is the length of it, and N, capital N, is the number of turns in the solenoid. Here mu r is the relative permeability, which is given as 100. Mu naught, the value of mu naught is equal to 4 pi. The magnitude of the value of the mu naught is equal to 4 pi into 10 to the power minus 7. Mu r is already given to us, which is equal to 800. Length is also known to us, which is equal to 0.4 meters. And we have to find the area of cross section. So here the area of cross section will be equal to 3.14 pi r square into A will be equal to 3.14 into R is equal to 3 centimeters, or 3 by 100 whole square. So from this formula we can find the self-inductance of the coil. So here it is a solenoid. So the self-inductance of the solenoid will be equal to mu naught is equal to 4 pi into 10 to the power 7 minus 7, sorry. Mu r is equal to 800. Now n square, here the number of turns is 500, so this will be equal to 500 whole square into the area of cross section divided by the length, which is in meters. So in meters it will be equal to 0.4. This length is equal to 40 centimeters, so in meters this will be equal to 0.4. Now area of cross section is, so L can be written as, this can be written as 4 pi into 800 into 500 whole square into 3.14 into 9 into 10 to the power minus 4, and here there is also minus 7. So this will be equal to minus 4 and minus 10, this is equal to minus 11 divided by 0.4. So the self-inductance of this coil will be equal to 4 into 4 into 800. This is divided by 0.4 divided by 0.4. So this is equal to, so the value of L is coming out to be 1.77 Henry. The unit of inductance is Henry. So the self-inductance of this solenoid is equal to 1.77 Henry. So I'm just writing the value of L here, that is equal to 1.77 Henry. Now here the induced EMF will be equal to 1.77 into delta I is equal to 3 minus 0 divided by delta T, which is equal to 0.4. So induced EMF will be equal to 1.77 into 3 divided by 0.4. So this is equal to 1.77 into 3 divided by 0.4. So this is equal to 13.275. 13.275 volts. So the correct answer here is A. So in this question, we were supposed to first of all find the value of the self-inductance of the solenoid by using this formula, that is equal to mu n square A divided by L, where mu is the absolute permeability of the solenoid, which is equal to mu naught into mu r, where mu r is the relative permeability and mu naught is the permeability of the free space. And n here is the number of turns in the solenoid, A is the area of cross section, and L was the length of the solenoid. So by using this formula, we have calculated the value of self-inductance, and then we have used the formula for the induced EMF, which is equal to L di upon dt, and which can also be written as L delta I upon delta t. So after finding the value of L, we were able to find the value of the induced EMF, which is equal to 13.275 volts. So the correct answer is A, which is equal to 13.275 volt. So in the next session now, I will be taking up the topic of mutual inductance. That is in the session number 12, we will be studying about mutual inductance. So till then, have a nice day. Bye.